So good morning, everyone, and welcome to today's Zoom session. Please bear with us an additional minute or so as we allow attendees to continue to join, but we will be getting started momentarily. Thank you. Okay, I do want to be mindful of everyone's time, so I think we'll go ahead and get started here. So once again, good morning and welcome to today's virtual session on RTI Rapid Dam Risk Analysis. My name is Patrick Ahern with RTI, and I'll be helping out with the virtual room today. Please note that your audio and video will be muted when you log in. If you have any content-related questions for our presenters today, please put those in the Q&A window. This will be the best way for us to see and address your questions as time permits. If you do happen to have any technical issues with the Zoom platform, please let me know in the chat window, and I can help with any troubleshooting. So again, I'd like to thank everyone for joining, and I'll now turn the meeting over to my colleague, Sean Carney. Sean?
All right, thanks, Patrick. Yeah, so let's go ahead and jump in here. My name is Sean Carney, and I'm going to be presenting today with Jonathan Quebeman. And so the two of us have about 20 years experience in water resources industry and are leading up a lot of our dam safety risk work with Tennessee Valley Authority, the World Bank, and others. And so I thought I'd start actually just talking a little bit about RTI, just since a lot of you may not be familiar with RTI. We're a large research institute, and we have a tagline this on here, this turning knowledge into practice. And so basic idea there, we feel like we sit kind of between the research and practice and applications. And so we have our hands kind of in both sides of that, and have been involved in looking at some of the cutting edge research on things, as well as trying to have practice, applying these in practice. And so we're a nonprofit organization. And so what that really means for this is really our profits that we do make on projects end up coming back in internal investments into different initiatives. And so some of the stuff that we're talking about today is funded by some internal investment. And we do have broad expertise across the Institute beyond just the Center for Water Resources, folks in economics and statisticians and data scientists. So within the Center for Water Resources, we've been around about 35 years or so. And so this is just some groupings of our different clients. So we have folks in the states, excuse me, federal level, hydropower companies, and then some of the international development banks and our international clients. So we've been doing projects that cover operational decision tools to planning studies, and then of course the dam safety risk work that we'll be talking about today. And so over the last 8 or 10 years or so, we've been working on different aspects of risk analysis and hydrologic hazards and hydraulics and consequences assessments, and have done different pieces from both the detailed analyses on the QRA level to support QRAs, down to screening level analyses, and then with the Corps of Engineers, we've been working with them to build some tools to facilitate doing some of the different analyses. And so we'll be talking about those a little bit later. So dam safety concerns, they're growing. We have aging infrastructure, there's encroachment on the dams, there's concerns about climate change and whether or not that's increasing storm intensity. So where are the greatest risks? If we're looking at a large portfolio of dams, and maybe you're a state regulator and have a large portfolio that you're trying to invest in, where are the greatest risks across the entire portfolio? And if we look at that portfolio, where should we pinpoint doing additional studies and really getting into the details on what's needed at different dams? If we're considering just a single dam, how do we know if the spillway capacity is sufficient, or how can we assess that? And so all these ultimately are asking the question, where should funds be spent? And how do we decide whether to address one issue or another, or focus on one issue or another? And so where does risk analysis fit into this whole decision-making process? And so we're going to be focused on risk today. And so we thought we'd just start, there are three main components to risk, and we can break this up a little bit differently, but the three main components are the likelihood of the loading, that there is potentially a large flood that could come and put overtop the dam, or there's a seismic event. There's also, and then there's the second component, the probability of failure given the loading. So given that a dam is overtopping or there's a seismic event, what's the chance that the dam could fail? And then what are the downstream consequences? If a dam were to fail, what would be the consequences downstream? Or if some component of the dam were to fail, there might be less consequences. And so those are the three different pieces of risk. And so we just wanted to talk through, just to start off, just to get our heads in this realm, a hypothetical example. And so if we're considering two different dams, one is located in an urban area, this dam A, and the other one in more of a rural area. And so which one would we think, just off the top of our heads, is the greatest risk? And so just put your mind there. And so what information do we have to support that when we think about these three different components of risk? And so we can, maybe there have been studies that have been done in the past, and we have some information about the dams. We know for the consequences that one dam, the one above the city, has a lot higher likelihood of life loss than the rural dam. But there still are people that are at risk in the below the rural dam that there could be some life loss below the rural dam. What about, so on the PMF, we may have done a PMF analysis for both of these, and maybe the dam above the city can't pass the PMF, whereas the rural dam, it has a large spillway and there's no problems there. But we don't really know what the likelihood is of that huge flood, that the probable maximum flood. And if we look at the condition of the two dams, maybe on the dam above the city, everything is in great working shape. It's been maintained really well because it is in the setting that it is. But the rural dam has some seepage issues. So, but we don't really know necessarily what the likelihood of failure is given that. So here we have just a little example of one case where there are two different dams, two different issues. So how do we look at that? How do we start to assess which one is the bigger risk? If I'm a regulator, which one is the bigger problem that we ought to be considering? So if we can start to put numbers behind some of these pieces, if we can say, okay, that PMF actually is more like a 1 in 500,000 event, or the seepage is actually a much higher likelihood that if there were an issue that could fail. So then that really, we can start to understand what's going on with those. And so what process just went through our minds there? So first we step through and kind of look at what failure modes are. We try to estimate the different probabilities. Maybe it's just kind of in our hunch, a concept of that, and then understand the consequences. And we, in our minds, can pull all that together and kind of say, okay, this one, actually, maybe this is a bigger risk, or this is a bigger risk. So that really is risk analysis there. Even though it's a very qualitative sort of sense, that is a risk analysis. And so risk, the federal guidelines, they take these three pieces, and it's the product of those, and sum that up over the various ranges, and you have an understanding of what risk is. So we can visualize risk in a number of different ways, but one is this FN chart. And so you can see here those same components. You have the consequences on the x-axis, and then the probability of loading and the probability of failure given the loading gives you the annualized probability failure. And so we can take this, and if there's the Reclamation and others have published these tolerable risk guidelines, and so we can look at where there's risks that we really need to address, which would be up in the upper over to the right side, and then in the green area that would be considered what maybe is tolerable risk or a more acceptable level of risk. And so we can take a given dam like this yellow dot and plot the total risk for that, or we can take individual failure components or failure modes and plot where those different pieces land. This is on the very quantitative level, but But we can take our example now, and we have the rural dam and the dam in the city. And if we plot those on this graph, just using those numbers that we had come up with, in this case, actually the rural dam ends up being at a higher risk than that dam in the city. And so as a regulator, you might focus more on, let's get this rural, the issues with the seepage addressed first before, and maybe if you have limited funds, focus on that one first. And so the federal guidelines, they have this graph, which just, I think, helps to put together the different pieces and how they all kind of fit together. So we have the failure modes identification, and then the risk analysis, which we're focusing on today, is focused on estimating what risks are. And that really, ultimately, that's not the end goal, though. The end goal is to assess how bad those risks are, and to make recommendations on what a decision should be. And an actual decision will have a lot of other factors play into it, but they all, ultimately, this comes back to having a good estimate of what risks are for a given location. And so another piece of if we just look at the FERC guidance, they've classified different levels of risk analysis, and the Corps of Engineers and USBR, they have similar classifications. And so they go from a screening level where you're looking across all the portfolios and you're trying to assess, where should I really focus additional effort in understanding risks, all the way up to a quantitative risk assessment where there's a single issue, a single dam, and we're really focused on what the risks are associated with a particular issue at that dam. And so I just wanted to emphasize here, there's an increasing level of effort going from the top of this graph, or this table, to the bottom, but there's also an increasing magnitude of the decisions. At the screening level, really the focus is, where should I invest additional funds to understand what's going on with the dams? And whereas on the QRA level, that's at the point where, do I need to make a major capital improvement investment? And so it can justify an additional level of effort to understand what the risks are there. So for the rest of this presentation, we're really going to focus on the probability of loading and the consequences given a failure, because those are the pieces that within the Center for Water Resources we have the most expertise in. That's not to say that the middle component isn't important. It's very important, obviously. But we're just going to focus on those two pieces and how those can play into these, into the different levels of analysis that we were talking about up here. And so we'll start with talking about QRAs and SQRAs and kind of how this fits in. So we'll start just with an example from Mactaquac Dam. This is up in New Brunswick. And for this dam, New Brunswick Power is looking at, they're undergoing rehabilitation over the next years. And so they're, as part of that assessment of what needs to be done, they were assessing their spillway capacity and seeing whether it's adequate or they may need to expand that. And so Mactaquac Dam, it's sitting on a large watershed. It's essentially a run-of-river. There is some fluctuation in the pool, but there are low incremental consequences if there were an overtopping failure of the dam or during a large flood. And so they're looking at a really big capital improvement investment. And so the question really is it, is the spillway capacity adequate? And so to start, they did an initial risk assessment. It was, at a more evaluation level. And so on that one, they found, it looks like the spillway capacity could be within the tolerable risk guidelines, and that it may be something that the existing spillway capacity is sufficient. But now, over the last couple of years, we've been working with New Brunswick Power and a larger team to assess that in more detail, to understand those risks, to see if where they should go with this project. And so we're in the midst of a full quantitative risk assessment or analysis. And so with this, like I said, we're working with a large team of people, and so they're undergoing a real detailed probable failure mode analysis that RAC and engineers and economists and Stantec and others are working on. And then we're going to be using DAMRAE with the full uncertainty for those of you who are familiar with that program. On the probabilistic flood hazards analysis, we have some partners, MGS Engineering and DTN, that have done a regional precipitation frequency analysis to really understand what the precip frequency characteristics are for the watershed. And we'll be using this, or we have been using the stochastic event flood model that MGS Engineering developed to assess the probabilistic flood hazards. And with that, we're doing a full parametric uncertainty analysis. We're looking at gate outages. We're looking at, there are some upstream dams and whether those dams fail or not. So it really is a very comprehensive analysis to understand what the loading is on the dam. And then from the consequences analysis, we've participated in some EMO interviews, the emergency management offices, just to understand how evacuations would occur and how warnings would get out to the public. And then Stantec is working on looking at the breach uncertainty, and then we'll be doing using LifeSim with full uncertainty to the specific PFM. So again, this is a case, they're at the point to evaluate, do we need more spillway capacity or not? And so it's a major capital improvement investment. And so it justifies doing a very detailed analysis to understand that. And so there are various tools that we've used or others have used. SEFM, like I mentioned, is one that we've used for this project I just talked about, and then TVA and others. And then on the consequences side, well, and HEC-WAT from the Corps of Engineers has a flood risk analysis option in it that can do similar sort of analysis as SEFM. On the consequences side, there are two kind of premier tools that are being used now. The HEC LifeSim tool that we mentioned earlier, and then Life Safety from originally BC Hydro and now HR Wallingford. So these are just some tools that are used on the QRA level. But there are challenges with doing a full QRA. It can be costly. It can take a lot of time and data. And then just to scale that up to a larger group of dams really may not be entirely, not really possible or really make sense because of the level of efforts that's justified. So let's move on to the SQRA level. And here, we're talking about different failure modes. And the idea is to use existing data and consequence estimates to understand risks. But really, how good are those estimates, and how does that influence things? And so, if we think just about the hydrologic loading, a lot of times we have a PMF, like we talked about earlier, but we need to make an assumption about how to translate from the observed record. This is, looking at the pool elevation, all the points over to the left of the graph may be observations, but then the PMF we just place out and make an assumption that, okay, maybe that's 10 to the minus 6. But how do we interpolate between the observations and that PMF level? Should we assume the PMF is actually a lot more common? Should we use a more gradual curve? So each of these assumptions, it affects the way we perceive the hazard associated with overtopping the dam. And then if we look at consequences, similarly, there's if we consider that's the green is the tolerable region. And so if we look at a particular failure mode, and maybe it's a 1E-5 level, and we've come up with a life loss estimate that puts us at about 20. Well, that's right on the border between the two. But if our life loss estimate is actually higher, just 100 people, or there's 100 more people that could perish in a failure, then you really shift your understanding of what the risks could be there. And it can really change. If you have rough estimates from that can really change the risk acceptability. So I want to talk a little bit just about what TVA is doing on the SQRA level. They are using SQRAs, but we've helped them to do really detailed PFHA analyses to understand the overtopping probability. And then we've done very detailed consequences estimates to look at that. But then they're using that information to inform where they take the different failure modes and how they place that, how you understand what the consequences are under a given failure mode, and how you understand what the the likelihood of failure is for those failures that have a hydrologic component to them. So there are various tools to look at that can be used for actually assessing the hydrologic loading and the consequences at more of a SQRA level or getting towards the SQRA level. And so I want to talk briefly about the RMC RRFT tool. And so this is a tool that we are actually helping the Corps of Engineers to develop. And so they've recognized the need to really improve their estimates of the overtopping probability for their different dams. And so we're building this tool. It's a web-based tool. And so the idea is you could upload a precipitation frequency relationship, or if you don't have precipitation frequency information already available, it will extract information from the NOAA Atlas 14 to get the precip frequency from that. And from that, fit probability distributions. You can upload a HMS model, and using that HMS model, hit the run, and it will go through, do all the executions of that, all the sampling that's required, everything, and then generate a hydrologic hazard curve for the dam. And so John's going to be talking a little bit more about that shortly. But just to go back, we talked about the QRA level. There's very detailed analyses that are justified. But then on the SQRA level, maybe it's not quite as justified, and the concept is to use information that's available. But I just wanted to use the TVA example and just point out some of these tools that are available that can be used to get to a more quantitative understanding of the loading, and also a more quantitative understanding of the consequences. And so that can help to improve those estimates that can then feed into the SQRA and help us have a better understanding of what those risks may be. So with that, I'm going to pass it over to John, and he's going to keep talking about some of the other phases.
Okay, good morning, everyone. Thanks for joining us today. We really appreciate your time and the opportunity to discuss some of these tools and processes that we've used for risk analysis. I'm going to move, Sean's talking about the QRA and the SQRA. I'm going to move to the level 1 and level 2 as referred to the FERC draft guidelines as shown here for periodic and screening methods. And really the focus here, if you look at it, is on prioritization of the inventory. And so what is it prioritization for? It could be prioritization for additional studies, excuse me. And so you want to look at the portfolio and understand what kind of studies should be used, what kind of information needs to be collected. Or it could be to look at your portfolio and identify some potentially very high risk dams. And so just gaining a base understanding either at the screening level or at the periodic screening level of these factors. And just in general, this is the minimal to lowest level for making decisions. Sean said full QRA is for very large investments and very large decisions that have a significant impact, whereas here we're talking about screening levels. And so there's different tools and applications that are appropriate at this level. And so we're really going to be talking about the tools and the systems that are available to help support quantification of the loadings and consequences that are used within the periodic and screening methods. All right, let's look at, this is from the ASDSO on their website, the dam failure mechanisms. And if we look at all types here, we can see that from this collection of statistics that overtopping is 34% of failures, and then we have foundation, 30, 28 for other types of failures. And this is good information to have when we're looking at screening levels to help identify maybe where we should focus some energy. But what I think is interesting, if we look at the incidence of the drivers, that the hydrologic and flooding condition actually dominates the incidents themselves. So it could be a piping and seepage failure, and it's because of a higher storage level that you've never experienced before, right? It's an extreme event. You've pushed the pool into the flood zone, and it leads to a piping failure. So the hydrologic and flooding conditions are quite an important factor when you're doing some of the periodic and screening levels. If you have limited, budget time to focus in an area, that's a pretty good area to focus in. We can also look at some of the site-specific data that's required for each of these. And so for overtopping, it's minimal. You need to understand something about the watershed, you need to understand the hydrology and the salient features of the dam itself, including your storage levels, the gate conditions, spillway discharge capacity, etc. But with that information, you can actually do a decent job of estimating the overtopping probability. Whereas the site-specific data for foundation or piping seepage, these are a lot more intensive. It requires as-built drawings, site-specific investigations, and scaling up to the portfolio level is challenging, or implementing periodic and screening methods does require more site-specific information. If we look at the epistemic uncertainty, sort of the knowledge uncertainty, there's ways that we can try to quantify that with an overtopping, looking at the hydrologic loading conditions, where again, with foundation and piping seepage, it's fairly high. So the point here is that the hydrologic and flooding conditions are pretty important when we're looking at the screening level, again, with limited resources to be able to assess this. So let's go to the quantitative side here, and let's look at the equation that Sean has been working through here. We have the probability of load, we have the probability of failure given load, and consequences given the failure. And so the question is, can we do risk-based methods and with quantitative approaches at the inventory level? So what are some of the challenges here? If we take the load, we might be looking at the PMF against the spillway capacity and simply asking, does it exceed it or not? But then there's a question, what is the probability of the return interval on the PMF? And that can vary widely. We can look at the statistical record, peaks of record, but the focus here might be on the 1E-3, 1E-5 levels, where we haven't observed those in the historical record. There's statistical approaches that can be used, but how do we scale it up to some of these other extreme events? We might be interested in gate failures or blockages. And so what are those? How do we incorporate those into the loading condition? The probability of failure given the load, there's generalized PFMs. We just looked at them on the, for overtopping failure or for, for piping, et cetera. But again, it does require a lot of site-specific details. There's a lot of uncertainty, and we're going to talk about a way to address that as we move forward with some of these rapid risk techniques. And then consequences given failure. There might be an EAP maps, but they only have the sunny day or the PMF. And we could be interested in some of these incremental levels of storage or various intermediate events, pre-breach flood events that we want to consider. Breach maps may not be available, and this is certainly the case as we move outward into more of the international sphere, where there's limited studies that have been done to estimate the consequences. And then continued development, as Sean noted, if you change from 20 people to 120 people, because there's now some new development downstream that can significantly impact your risk profile. So we're going to be talking about this general class here that we call rapid risk analysis, and essentially this is an extension of some simplified quantitative methods to support assessment of different components of risk at the inventory level that could be used for screening and periodic reviews. And so what RTI has developed, we have a suite of tools, all right? We call it the RTI Rapid Risk Suite, and we can break it into, and we'll be focusing on the probability of load, and there's two main components, RTI WexGen and RTI QFreak. And then the consequences given the failure, again, there's a set of tools, RTI breach and RTI impacts. And the point of building these is that these applications allow some of the loading and consequences information to be scaled up rapidly, and it makes it much more accessible. It's cost efficient and time efficient, especially as we start to scale upwards in size. And so first we're going to focus on the probability of load and talk through how we can look at inventory level probabilistic hydrologic loading conditions. So we're moving from this deterministic, or we're looking at it from this deterministic approach, which could be a design storm approach or an AEP neutral approach, where we have a PMF event, we have historical events, or we have design storms. Something to remember, though, is that not always, the 100-year precipitation may not always equal the 100-year flood, right? That's the AEP neutral approach, and it can be a good approach if you have good initial conditions, but your initial conditions actually vary. If we're looking at starting pool levels, what's the probability of certain storages within the dam of interest or some of the dams upstream? What are your initial soil moisture? Is it dry? Did you just have an event? The probability of those soil moisture conditions change. And the temporal patterns for the precipitation itself also vary. And all of these can impact. You can have a 100-year precipitation with a much larger flood response or even a smaller flood response. And so that process of evaluating that is moving us towards a PFHA, a probabilistic flood hazard analysis approach, where we actually can assign some annual exceedance probabilities to metrics of interest. This could be your inflow levels, this could be volumes of inflow, this could be your reservoir levels. And we can gain a better understanding of what the probability of exceedance is for those different extreme events. So the PFHA process requires quite a bit of data. And so these dashed boxes are major components that need to be input into the algorithm here. So for example, we need to look at the storm depths and templates, the storm depths being the precipitation frequency. And so we have to sample from the precipitation frequency, and then we apply it to the watershed and scale it over the different subbasins. And we need to understand the temporal and spatial patterns of that event, which can vary significantly. We also need a set of initial feasible conditions. This is the soil moisture, snowpack, et cetera. And so those feed into a hydrologic model. We then run this, develop the hydrology, put it into a reservoir model or models, and repeat this process thousands of times, sampling from this information. And then we collect all the outputs, such as peak pool elevation or peak pool elevation, inflow levels, volumes in inflow, and we aggregate it to create these hydrologic hazard curves. The challenge here again is how do we get all these components, and then how do we do it at portfolio scales, right? This is the RRA approach that we're discussing here. And that's where some of the tools, the RTI WexGen and the RTI QFree can come in, is the development of these to scale rapidly. So one of the first pieces is the storms. We need to understand the precipitation frequency relationships that we sample from. There's some excellent work that's been done by MGS Engineering and DTN for developing, doing storm transpositions and doing frequency analysis and even storm typings to develop this information. And if that exists, if you do have a regional precipitation frequency relationship, that information could be used. But in a lot of cases, that information doesn't exist. And so you can use within the United States something like Atlas 14 or AORC gridded data, or internationally, you can get into MSWEP or even ERA5 to just try to get estimates of, of some of the extreme precipitation events. Excuse me. The other piece here is the storm templates. And so this is how do you scale the precipitation and apply it both spatially and temporally across your watershed. These again can be developed using remote sense data to develop estimates. Again, if you have good information, storm transpositions and other templates to use, by all means you can use it. But if you need a rapid set of templates, these can be scaled from the available information. We also need to look at storm seasonality. And so this is when do the maximum events occur? And this is very important because is it a spring dominated or a monsoon dominated event? And so we understand the timing, and the timing is important because that affects the initial conditions, including your snowpack. What is the approximate level of snowpack, the starting level within the watershed? This also affects your reservoir levels. Again, looking at the season, where is it? We can sample randomly from these distributions of starting pool levels and use that to initialize the models for each one of these simulations that we prepare. And then finally, we can look at the initial soil moisture. We're just showing here the CDFs of soil moisture. And so we can sample from those randomly, apply it to the watershed, again, by month. And so all of these are used to develop some of the inputs. One of the other components here is the HEC HMS models or the hydrologic models. And so we've created this application with RTI QFreak for an automated HEC-HMS model development. Again, I want to emphasize here, if you do have existing HEC-HMS models, by all means, they can be used. But in many cases, if you have a dozen dams, if you have 100 dams, 1,000 dams, you may be interested in developing these rapidly to at least develop some initial estimates. And so we use the base hydrocorrected DEM, dam locations, salient features of the reservoirs and the dams, and general land cover information, and that results in automatic production of these HEC-HMS base files. And they're parameterized with time area unit hydrographs, green amp losses, and includes regulated flows, not just at the dam itself, but also looking upstream. And that's an important factor, as we can include the reservoirs upstream of the subject dam of interest as well. And very rapidly, we can create hundreds or even thousands of these HEC-HMS models. Again, if you have a smaller portfolio, we can work with existing models, but if you do need to scale up, it's certainly possible. And so with those pieces, we can then begin the sampling. We understand the meteorological environment, we understand the initial conditions environment, and we have the processes built to do the samplings. And this is the sampling process itself is really the kernel behind the tool that Sean mentioned, which is the RRFT, the Army Corps' RFT application, which is taking the HEC-HMS models and doing this sampling process. And the outputs from that are these hydrologic hazard curves. And so this allows us to get estimates of the annual exceedance probability. And so, for example, here at this sample dam, we can see that there's an overtopping AEP of approximately 1E-5. And that's really informative to know that it's about a 1 in 100,000 year compared to if the dam was showing overtopping at 1E-3. And you might have a different set of actions for dams that show more common overtopping probabilities compared to more rare overtopping probabilities. Now let's go to the other side of the risk equation here and consider some of the consequences given failure. Again, in the light of rapid risk assessment or analysis, and at the screening and portfolio levels. So how can we assess the consequences efficiently at scale? So similar to the HEC-HMS model process, we also have developed this automated 2D HEC-RAS model development. If we take base DEMs, dam locations, land covers, we're able to rapidly create these RAS models. I also want to emphasize here, if you do have site-specific RAS models, we can use those, right? This whole process is extremely modular. But if you do have a large portfolio, you need a rapid estimate of consequences, this tool can easily scale up to the portfolio level. The runtime data include the hydrographs, the breach hydrographs per scenario, which can include variable pool starting elevations or pre-breach flood events. And so we can run all of those scenarios, and the outputs are the RAS model itself, which is an actual product, in addition to the results, which are the breach scenarios, including the depth and velocity grids as we move downstream. This isn't, I will say this isn't as robust if you're doing site-specific breach models, but this is, the intent is to scale it up. Is how do you move this to the portfolio or inventory level, allowing us to create hundreds or even thousands of these models very rapidly. And so with that data, let's just take an example here. If you do have 100 dams and you have 5 scenarios per dam, you have 500 sets of results that need to be processed. And so we've automated in a simplified way, again, for rapid screening, these automated RAS output processing. And so we are able to develop estimates of the population at risk, life loss, or other economic losses for all of these scenarios, and develop summaries for all these cases for each one of the dams within the portfolio, and ingesting a number of different data sets. Just a few examples here. If you have a structures database or OpenStreetMaps, National Bridge Inventory, or other land covers, all this information can be used to help develop estimates. This is, again, I want to emphasize, this is not as robust as FIA or LifeSim, like Sean has mentioned, but this is a way, again, at the screening level or the periodic level to develop some of these estimates. So let's look at just a few case studies for some practical examples of how you could apply these tools. And so looking locally here in Fort Collins, the question might be which dams in this area are at highest risk of overtopping. And so what can be done is using the RTI QFreq, and there's an existing set of precipitation frequency relationships, Colorado, New Mexico study that was completed by MGS and DTN. And this information could be applied within the sampling routines once we have the hydrologic models for all these dams. And that would develop a portfolio level assessment of potentials for overtopping, both the inflows, the volumes, and overtopping potential for these structures. Let's look at consequences. And I want to say you could just do you can just do the overtopping probability. You don't have to do the full suite, right? It's very modular. And as we move into the consequences, you might be interested in just the consequences estimation to ask questions of which dams, should it fail, we're assuming it does fail, which ones have the greatest impacts at different levels. This would be a combination of RTI breach and RTI impacts. And so we can scale these up to the portfolio level to develop estimates of population at risk, life loss, both for the direct impacts because of the breach, but also indirect impacts. There might be recreational losses, lost flood protection benefits, et cetera. And these can all be quantified. Scaling up to the portfolio assessments, we might ask questions like, what are the estimated benefits, benefit cost ratio for a set of investments for dam safety improvements at the portfolio? Or similarly, if you have a set of fixed funds, which projects should be prioritized across a portfolio? And this is part of the RTI impact suite. And so you can develop an EFA, an economics and financial analysis, develop capital improvement options, et cetera. And again, this requires that middle piece of the risk equation. This requires understanding the fragility, the probability of failure given the loading itself. But if you have those estimates, this can be scaled up and you could look at the reductions in risk from certain investments. The middle piece I want to talk about briefly here because it is highly uncertain, and it can be an intractable problem trying to scale this up to the portfolio level. It's to try to address that. RTI recently has developed this online risk application. We call it the RTI, the Interactive Risk Calculator, and we can ask questions like, how does the risk change if the overtopping SRP changes? And so, for example, we've broken out here 3 different dam types. We have earthen, masonry, and concrete, and we're able to change the SRP relationships and then identify how that impacts the risk. There's a lot of uncertainty in those, but at least we can see what does it do for prioritization. If you move your SRPs in a certain direction, do certain dams still remain at the top as a high priority for potential overtopping failures? And so it allows us to interact with both the probability of the load and the consequences to estimate some of the risk. We can also, within the calculator here, ask questions like, what if we adjust the AEP? And so in here, we can put in elevation thresholds. If you add a new spillway, this is going to change the probability of different reservoir levels. We can see that it shifts, and we have a shift here. And the annualized overtopping P failure will change. And so that value will interact, and we can see the impacts of adjusting the AEP. And you can also compare it if you do have estimates on earthquake or stability P failures or other modes. You can do comparisons between these to identify which one is the most significant and where should efforts be focused. And then taking that up to the portfolio level, we can look at SRP. So we've done the SRP sensitivity and the AEP sensitivity, but looking at how does that impact the portfolio as a whole. And so we can compare individual dams in this FN, where here N is the economic consequences, and looking at the annualized probability of failure that's aggregating across all these modes. And we can look at individual dams in more detail. So moving forward, when we do the risk analysis at different levels here, we're looking at the probability of some event and the impact. And so if you quantify these, you can kind of get a sense of which one of these 4 classes you're in, right? and understand the portfolio a little bit better. But it's important to remember that the questions should be proportional to the methods employed. If you have a very large capital investment decision to be made, the rapid screening approaches are certainly not appropriate. But if you do have a portfolio and you have limited information to support prioritization across the portfolio, you may want to look at some of the rapid screening methods that we've discussed here to at least get that initial idea. And again, this is quantitative, right? This is not just working with the information you have, but we're using quantitative methods to develop some of these estimates, both on the probability of loading side and the consequences given failure. And if you have fragility, that can be aggregated into estimates of the risk. And it can be scaled up at the portfolio scale, right? A lot of these tools and processes exist, but they're on a dam by dam basis, whereas here we can implement these to a much larger scale in a very cost and time efficient manner. And so with that, I think we'll stop here and we will open it up for questions. And so thank you very much.
Awesome job, John and Sean. This is Katie Van Werkhoven. I'm going to help out John and Sean fielding some of the questions that have come in. The first one, a common question that comes up, are these rapid risk assessment tools free online? John, do you want to quickly address that?
Yeah, so some of the components, the tools here obviously are modular, right? There's pieces that we're working with, including HEC-HMS and HEC-RAS, and so those components are freely available. The system itself to develop these the estimates of risk and develop precipitation frequency relationships, et cetera, are not freely available online. Some of the applications, such as the roofed application, the RRFT with the Army Corps of Engineers, eventually will become in the public domain, but right now they're still proprietary applications.
Yeah, the goal of the Corps with the RRFT tool is they're doing the development internally right now, but yeah, the goal ultimately is to make that into a publicly available tool. Awesome,
thank you. Another question that comes from Scott Bryant with the City of Raleigh. Are there similar risk-based tools and other methods to assess potential removal of dams, assuming that the benefits realized from the original construction have changed or may not be as viable going forward? Good question.
Yeah, and I saw that a second ago and just have been thinking a little bit about it. So I mean, I guess that's a great question, and I think we talked about a lot of different tools today, and so I think they're definitely that gets into a number of different pieces here, and we've been talking about dam safety risk, and so considering like overtopping probability and how that that there's a risk to overtopping failure. But I think you point out here or in the question that there's benefits to the different dams. So while you may want to remove a dam because it has a high overtopping probability, right now it's providing some amount of flood benefits to a city or something, assuming that it's upstream of a city. And so there's a trade-off there between the benefits of the what the dam is providing in terms of flood reduction in flood risk for more common events and the potential what it could be doing. So with some of the hydrologic hazards analysis, we're with the hydrologic hazard curve, we really are getting the probabilities from the common end all the way up to the really rare end. And so you can see for a given dam, what's the what sort of benefit is it giving in terms of reducing the downstream flows for more common events, and what are the consequences, or what are the increased risks at really high events when a dam could fail. And so there definitely I think we could run a hydrologic hazards analysis with the unregulated basin, essentially a basin like with the dam removed, and look at what the risks would be of a particular flow happening and then you could run it with the dam in place and see the difference between those two. And so it can help to assess just that question there, both how much are we reducing the risk by removing the dam, but then what are we losing in terms of the flood control benefit. Obviously, there are other aspects of what a dam is providing, recreation and fisheries, or water supply or whatever, that may be it, that would be a separate analysis. But in terms of the risk analysis, yeah, I think the tools can help support that. And which tool is appropriate, that's getting into more detail on particular dam and what sort of questions are being asked and at what level we're at.
Yeah, and I think this is just real quickly here is an important point to remind everyone that the QFreak application is not necessarily dam specific, it's hydrologic specific. And so if there's a town or a village or a point that you want to evaluate some of the hydrology and the return frequencies, that application could be applied. It doesn't have to be for a dam.
All right, and another question here. Do you look at only hydrologic risk or look at materials of the dam and foundation, liquefaction, foundation failure, etc.?
Yeah, so the focus here is obviously on the hydrologic. And the reason being is that if we look at the ASDSO stats, we look at the incidents, the driver of the incidents, they're dominated by hydrologic. Now, it's not to say that the properties of the embankments, the soil properties are not important. Of course they are. It's extremely important. It's just that it's very hard when we're looking at the portfolio level to scale up. If you do have site-specific information, so for example, let's say your portfolio, and I use that term liberally here, your portfolio is 3 dams. And that's fine. You can still apply some of these applications for 3 dams, but you also might have additional resources to get into some of the more site-specific investigations, looking at doing a stability analysis, looking at soils, pulling out as-builts. And if that information does exist, it can be ingested within this process here. Right? We're looking at the front end on the hydrologic loading, but there's also a lot of other components of risk, including the stability or seismic hazards that can also be ingested, again, if you do have that site-specific information available.
I think, just the emphasis of what the tools are that we've built is on hydrologic loading and on the consequences piece. And we've touched just barely on the middle piece, but we're not a bunch of geotech engineers and everything, and so we rely on others who have that expertise really to do that side of it.
Awesome. And then I think you started touching on this, John, a bit with the application to a smaller, large number of dams. But one question is, the application of those methods focus on small dams. Is it applicable for a large project as well? That's kind of a different take on that.
Yeah, I mean, I think this gets into which tools. We talked about a bunch of different pieces, and so for a single dam, yeah, we could use this stuff, and so either the rapid risk stuff that John has talked about, or some of the more detailed tools that are available, or not more detailed tools. Some of the other tools that are available that aren't necessarily aiming at the portfolio large number of dams. And so if you have an existing, if there are existing models, we can use those models. If there are depending what sort of questions we're wanting to ask, it may be more appropriate to look at using SCFM or using the RMC RFA tool. That's a separate rapid tool that if there's a hydrologic loading, you have that information already, or I'm sorry, the inflow loading. And so there's different tools, but yeah, definitely we've used we've been working with TVA and using SCFM there. Those are very large dams there, down to looking at different portfolios. But even at the portfolio scale, I think some of the stuff you've done in India, John, is that's looking at large dams across a large portfolio.
Yeah, for sure. Just real quickly here, that's also the emphasis of the RRFT, the Army Corps' RFT tool, which is site specific. If you have a single dam, you have a good hydrologic model, and you would like to understand or develop the hydrologic hazards curves, that's the whole point of the application. What we've done with the Rapid Risk Suite here is we've taken that and we've scaled it up. We've batched it so we can apply it to the portfolio level. But if it's a single site, you have a good hydrologic model, the roughed application would be excellent. And the outputs from that can go into an application like RMC RFA, the reservoir frequency analysis. And so you can link those and couple that information to get a better understanding of site-specific dam hazards.
All right, and a question coming from Ty from DTN, I believe. How prevalent are these techniques being used internationally, and where does the US stand with respect to regulatory use of these techniques versus deterministic approaches, and how quickly are things changing? So a three-part question there.
Yeah, that's quite a question, Ty. So thank you. Let's look at the prevalence of the use. I mean, they're not prevalent, and so let me take a step back and talk about the genesis of some of this. You know, our RTI, as Sean has alluded to, we do with a number of partners, a lot of different risk work and risk studies, et cetera. And so I've been working heavily in the international sphere, and there's a demand, there's a need for this type of study and these types of applications. The problem is that working internationally, the data availability, the quality of information is nowhere near like what we are blessed with here in the United States. We have ready access to flow data, precipitation data, radar information, and it's all very reliable. But yet there's a lot of countries that, in India certainly being one of them, where I've done quite a bit of work, where the information is not available, or it's the quality is challenged. And so because of that, we still needed to assess and scale up the process to develop estimates. Again, we've done studies on the prioritization of different projects and interventions at the portfolio level using some of these approximation techniques. And so there's definitely a demand. And because of some of the work in India, we are now engaging in other regions internationally to help move this one step closer to being able to answer these questions. It's very, for us, I think it's in the United States, we can answer questions quickly about how many people are downstream, how many people are at risk downstream because of the information we have available. But certainly in other regions of the world, it's hard to develop an estimate. It could be 100 or it could be 100,000. And so we need something to at least put us into the order of magnitude. And that's really where these tools are being applied, or there's a need to apply them. So I think I've answered some of the components of your question, Ty, but we can follow up on that as well. Sean?
I was just gonna say, you've talked internationally, that there's other parts of, Australia or Europe where I think, I'm not as sure about some other parts, but those in particular are definitely using the probabilistic methods and that sort of things. You've been referring a little bit more towards less developed countries, I guess. You also, I guess, Ty, I pulled up the questions, but another piece of that was, where does the U.S. stand with respect to regulatory use of these techniques versus deterministic approaches? And that's with respect to the federal agencies, the Corps of Engineers and Reclamation, they are already have been using risk for some time and using probabilistic approaches, or moving towards that at least. And then with FERC, I know that has been shifting, and even just over the last months, there's been some shifts there. And John, I don't know if you may have a little better picture of that, but that they have been talking about moving that direction and incorporating some risk-based information into the FERC regulatory process. But you want to?
Yeah, certainly. I mean, that's we did show the FERC, and we showed the level 1, level 2. Level 1 being screening level 2 being periodic, and the periodic is looking at more site-specific PFMs. more of a PFMA process, and using that as part of the Part 12D screening or Part 12D process. And so I don't know the timing on that. I'm sure some people at FERC have a better understanding of when that will come through, but some level of risk assessment under the Part 12D program is going to be required. And so these tools can be applied there. And again, if it's site specific, if you have a local HEC HMS model and you want to use RMC, RRFT, by all means, that's a great application for developing your flood hazards analysis or assessment. Analysis. And if you have a HEC-RAS model, fantastic. You can look at the consequences. So it's different scales. There's different questions, and what's actually accepted or not accepted, we're unsure of. But we've definitely talked to FERC about some of these applications already, it's certainly promising, especially on the RRFT side, to use such applications to help support that process.
I guess maybe the last piece of Ty's question was, how quickly are things changing? We've talked about some of the RRFT work that we've been involved in from the Corps of Engineers. So I know the Corps of Engineers is definitely investing a lot in improving things. Ty, we've been working with the SCFM stuff, and there are ongoing improvements there with SCFM and some of the techniques, in particular with precip frequency and all that you guys are involved in, and improvements to some of the sampling techniques and all that. And so, I mean, that definitely is an area, I think, with the changes at FERC and all that, it seems like things are continuing to, tools are improving, becoming more readily available.
Great. I want to acknowledge the time. It's 12:01. We'll continue through the questions as they come up for another few minutes to get through all those that have come in.
Yeah, go ahead, Katie.
Oh, go ahead. I was just going to say, well, if we get a lot more questions, we'll absolutely answer them after the fact as well and follow up with you.
Most certainly. And we also have our email addresses up there.
Yeah.
Certainly feel free to reach out with any questions, and we can follow up.
So there's two more that it seems I've missed at this point. One, going back to an earlier topic, I think we've already answered this, but I want to make sure I get this question out there. How are the risks of abutments and reservoir slides incorporated into the analysis, into the rapid risk analysis? That ties in with an earlier question, I believe.
Yeah, I think that ties in with the question on the probability of failure. And so, we are focused on the loading and the consequences, and less, not really on the middle piece of what the probability of failure given the loading really would be.
Right. But we can partner with others to do a full analysis on that. Yep. Last question up here at this point is, how long does it take to study an area for specific planning of hydropower towns and cities? And have you applied this technique, and how was the outcome?
Yeah, so I'll touch on that briefly. I think if you're using a standard site-by-site kind of approaches, that if you do one dam, it takes X amount of time, and if you do two dams, it takes 2X amount of time. It's a really hard scale. I should say it's a linear scale. And so it really depends on the size of the portfolio and also the level of detail that's being used here. It's not linear, right? There's a sunk cost for developing base data sets for one dam, but then as to do two dams, it's it's an incremental cost in both time and effort to do this. I will say though that certainly as you scale up, it's extremely more efficient than doing a site-by-site analysis using some of these for the screening level approaches. So how long does it take? Again, it highly depends on what information is available, where are we in the world, and what level of analysis is required.
All right, and the second part of that was, oh, sorry, go ahead, Sean.
I was just going to say that, I think that's a good, if there are specific questions there on a specific area, I don't think John was trying to just dance around the question entirely, but there are a lot of variables there. So, feel free to reach out to us, and we'd be happy to talk more.
Mm-hmm. But the approach you guys have developed is not as linear with respect to number of dams, particularly in some pieces of it.
Exactly.
Yeah,
Yep.
it's intended to make that scaling process much easier than a site-by-site analysis.
Correct.
And the second part of that is have you applied the technique and what was the outcome?
Yeah, I think one of the one of the great examples, and I've mentioned this already, but is some of the work that we've done in the India sphere, where we did have several hundred dams we were looking at. We developed Tech HMS models. We went through the full process, and that's why it's a good example. We developed the RAS models, did the breaches at various incremental steps within the pools, and used that to do a full economic assessment to justify or look at a number of different interventions within this sphere. And that was a really good, successful case study. So it worked well, it scaled well, and it was extremely efficient. Actively right now, we are doing different components, working on some of the frequency analysis or looking at the consequences side. So we're breaking it out into pieces. Again, the tools are meant to be modular, right? What do you need for what application, for what questions are you asking? But the India case study is a really good example of what's been built and how the whole process was used across that portfolio.
And can we are also doing some internal analyses to verify the approach for some locations we're very familiar with. Is that correct?
Yeah, that's a great point,
Yeah.
Katie. And we'll be publishing that as soon as it's available. But we are actively developing some verification on the process to compare it to more robust techniques and see how does that compare. And so as soon as that's available, we can certainly share that and provide links.
Oh, and another question from Garrett Jobsis from American Rivers. Are there applications for a state dam safety program which regulates, say, 600 high hazard dams? To point examples to point to, or anecdotes where you know that may be on the horizon?
Yeah, Sean?
We've been in some conversations with a couple different states, and we're actually with one in particular. It sounds like that is we should be under contract shortly to start doing some work there. So
yeah, there will be examples,
right?
Hopefully soon, but not
Right.
yet,
yeah,
Garrett.
So there are a couple different states that have expressed a lot of interest.
Yeah.
So in one case, there is something that we should be working on within a month or so. And then, the others, everything with the COVID and everything makes
And the number of dams, Sean, is on the order of 600. That's kind of the scale of portfolios that's in the realm.
That one actually is, well, I guess, yeah, there's one aspect that's, around that size, and then
right, just order of magnitude size. We're talking about large portfolios. Yeah,
hundreds to say 1,000 or so.
Let me also just kind of expand on that a little bit, which is, are there applications for the state dam safety program? And I just think from that perspective, let's take it from the state's regulatory perspective, which is, yeah, the applications are going to be, you have limited resources for investigation. You have limited staff. You have 600 dams in your portfolio, and you want to know where should you do where should you spend your time to do your investigations? If you can only do 30 dams a year or 50 dams a year, which dams should you focus on? And so in that case, it's taken from the regulatory side to say which ones are the highest risk and where should our limited human capital be invested in assessment of the portfolio.
Yeah, and just to follow up on that, I mean, I think we recognize that the state dam safety programs are kind of a unique place, that there's a need for, that there could be a lot of benefit from doing some of these portfolio-wide assessments of hydrologic hazards or consequences that may not have been done previously.
Yeah, and a question came in about the cost of that, and I'll preempt. Cost is very dependent on which components we're talking about are being implemented. It could be it could be simply the hydrologic hazards. It could be both hazards and consequences. Any more on that, John or Sean?
Yeah, I mean, again, it's not linear, and so going from 1 dam to 600, there's obviously some some cost in that, but it does vary, and it depends on what level of analysis is going to be done.
Right, but we're not talking about QRA for each one of those 600 dams.
Correct.
Yeah. That is all the questions that are up there. Again, if anyone comes up with questions after we all sign off, you see John and Sean's email addresses there. Please feel free to reach out. Thank you all for listening. Any closing thoughts, two of you?
Well, thanks for giving us your time, and hopefully there's something here that you learned, and feel free to reach out. We'd be happy to talk.
Yep. And we're very excited by these tools. We're very excited by the potential applications and how they could be used, certainly in the United States and around the world. And so we're very excited for the opportunity to share it with everyone. So thank you.
All right. Thank you both. Great presentation.
All right. Thanks.
Thanks, everybody.
Bye.